So if you recall last time, I kind of talked about what a monitor was, kind of the history of monitors real quick, talked about what a monitor object, built-in monitor object is in Java. And what we're going to do now is I'm going to give you a motivating example where the lack of this stuff causes problems, and we'll talk about some common concurrency problems that arise in this context. So by the time you're done with this part of the lesson, you'll understand some common synchronization problems in a buggy concurrent Java program. And as you'll see, this program has problems because it's going to be calling offer and poll in two threads on a queue that doesn't have any synchronization, protecting its internal data structures, its fields, and as a result, chaos and insanity will ensue. We'll see that when we run the test program. Okay, so you'll also get a chance to learn about some common complexities of concurrent programs, some of which we've talked about before, like race conditions, but we'll also briefly talk about deadlock, as well as starvation. You'll get a chance to learn about starvation as well. So let's talk about this app. So this is where the app is, and it's pretty funny because it's quite overkill to write a piece of code that's buggy. So if you go here, you can play with this app. I'll run it for you in a second and show you what it does. And what it's trying to do is it's trying to have a pair of threads, producer thread and consumer thread, that want to pass messages back and forth via a buggy queue. And as you'll see, it doesn't work very well intentionally. The actual interface is modeled to some extent on the Java array bounded queue class, which we've talked about before. And the part that we're dealing with here are the offer and poll methods. We've talked before about take and put, which are blocking, but an array blocking queue also offers an offer and poll method, and we'll talk about what their semantics are in a second, or what their intended semantics are. Here's a UML sequence diagram, it's a UML class diagram, that shows the design of the buggy queue. So we have this interface called a bounded queue, which is, again, a subset of what you would find with an array blocking queue. And it's got methods like put and take and poll and offer, is empty and is full, and so on. And then we have buggy queue, which is basically an implementation of this interface. And you can go here and find both of those pieces of code. Here's a sequence diagram that shows how things work. And I'll show you a little bit of this code here in a second. So basically what happens is we have a buggy queue test, and this test goes ahead and creates a producer thread and a consumer thread, and they're going to try to coordinate their actions through a queue. And then the run methods are called on both of these threads, and they run in a loop, and they basically do offers and polls. But since these are not synchronized, then chaos and insanity results. And so something bad will happen, and I'll show you what the bad things will be. If we were to open up buggy queue and run the unit test, hopefully it'll work. Probably should have tested it before class. Okay, good. It blows up right away. So let me enlarge that for you just a tad. It's maybe a little hard to see. You'll be able to see it in the video. So it's throwing an error in this thing, and that's of course because it's not working properly, and the values that are coming back are not what's expected. Let me try to run it again. Sometimes if you run it a couple times, it'll do different things different times. So what this test does, by the way, just so you know what the test is doing, is it's let's see, let's go open the test, buggy queue test. So what it's doing here is it's got a producer and it's got a consumer. Those are both runnables. They're going to share a blocking queue, except it's a bounded queue, not a blocking queue. And what they're doing here, the producer is going through for I equals 0, I less than max iterations, and it's going to offer something to the buggy queue, which is trying to put it in the queue. And assuming it works, it increments a count. And then the consumer basically is going to run, and it's going to call poll. Offer is a call that will try to put something in the queue, and if the queue is full, it'll return false. If the queue is not full, it'll put something in the queue and return true. Poll basically tries to take something out of the queue. If there's nothing in the queue, it returns null. If there's something in the queue, it'll return whatever was in the queue. So this piece of code here, which runs in a separate thread, will sit there and get the first non-null value, which may have to spin a while because depending on the order in which these things occur, there may be something or nothing there. And then it goes through for I equals 1, I less than max iterations. It does the same thing. It polls. It checks to see if it actually got something back. If it did get something back, it checks to make sure that the entries are ordered. And then every so often, it basically prints something out. So because, as you'll see in a second, this is a buggy queue, this is not going to work properly. Here's the test program. We make an array of 2 threads. And one has the producer runnable, one has the consumer runnable. We go ahead and start the threads, and then we wait for them to join, and then we record however long it takes to run. So that's basically the program. And as you can see, it crashes, which is exactly what we want to have happen. Now let's talk a bit about the implementation of the buggy queue, and you'll see why it's buggy in a second. So here's the implementation. Buggy queue implements bounded queue, this interface. I'm only going to show you a couple of the methods here. Under the hood, it's implemented as a linked list. And notice that offer and poll are non-synchronized public methods. So what will happen when you call them is that they will offer check to see if the queue is full. If the queue is not full, it adds the item and returns true. If the queue is full, it returns false. So it's offering but not blocking. And poll check to see if the queue is empty. And if it is, it removes it. Sorry, if it's not empty, it removes the item, first item. If it is empty, it returns null. And of course, this is danger. Anybody ever see the movie Lost in Space? You probably never saw the TV show Lost in Space, but this was a 1960s movie. I watched it when I was real young. And it had this little robot. And this robot would wave his arms and say, danger, danger, Will Robinson, danger, right? It was completely cheesy, but we didn't have much else at that time, so that was great when you're like 6 years old. And so when you see code like this, you see code that does not have proper blocking, proper synchronization. It's danger, danger, Will Robinson, danger, beware. It's going to be a problem, right? Okay, so given all that, the question is what's going to happen when you run it? Well, I showed you what happened. Bad things happen. And lots of different bad things happen in this particular case. Here's one thing that often happens, depending on the race conditions. It may turn out that your code will crash when you try to unlink something, and that's because the queue is left in an indeterminate state when 2 threads simultaneously come in to modify it. One is trying to add something to the queue, one is trying to remove something from the queue, and the implementation out of the box doesn't do anything to stop you from doing bad stuff. And so, depending on the implementation of the underlying class, like the buggy queue class or the linked list class, you may crash like this, it may hang, just weird things will happen, right? Because it's not meant to be correct. And the reason why this is the case is because the linked list class, as it says very distinctly in the documentation, is not synchronized. So if you read the documentation for linked list, it says, if multiple threads access a linked list concurrently, and at least one of the threads modifies the list structurally, it must be synchronized externally. In other words, you have to provide the synchronization. It won't do it itself. And then it goes on to clarify what a structural modification is. It's something that either adds or deletes an element into the queue. Setting the value of the element is not a structure modification, but changing the queue, adding or removing it, which is what we're doing here, will cause all kinds of problems. Okay, so just as a little, kind of synopsis of this, kind of stepping back one level, concurrent programs are hard to develop and debug due to a variety of different reasons, and there's some good articles that I'll point you to that give you more information about this. One problem is deadlock, and deadlock occurs when you have 2 or more threads where each thread is trying to acquire a resource that the other thread owns and won't give up their resource till they get the other one, right? So it's often called circular waiting. And here's a good example. We have 2 threads, T1 and T2, and 2 locks, L1 and L2. And let's say, for sake of argument, that T1 owns lock 1, so it's synchronized or acquired it. And let's say, for sake of argument, T2 owns lock L2, it's synchronized or acquired it. And now T1 needs L2 and T2 needs L1. Well, if they don't do anything to the contrary, they're going to deadlock because this guy owns L1 and he won't give it up till he gets L2, and this guy owns L2 and won't give it up till he needs or till it gets L1. So that's deadlock. Deadlock is actually pretty easy to detect because your program just hangs. You're like, what the heck's going on? And there's a bunch of ways to get around deadlock. The most common way to do things is to acquire your locks in order from, say, lowest to highest. You have to number your locks and have a rule where if you own a lock and you try to get another lock and you can't acquire it, you have to release things. There's a bunch of ways of doing deadlock detection and deadlock avoidance. Another problem is called starvation. And so the problem here is the thread is perpetually denied the necessary resources to process its work or to do its thing, right? So here we might have some thread that's running. It's the running Java thread. We may have a bunch of other threads that are higher priority threads that are waiting. And when the running thread is done, one of these high priority threads is going to get a chance to go. But there may be one core thread, or more than one core thread, who never gets a chance to run. So it ends up starving, right? It becomes weak and emaciated. And the reason there is because the other threads are always getting a chance to run, and that core thread is not given a chance to run. So that's called starvation. And there's a bunch of different ways. And in fact, we've been talking about things like fair versus non-fair locks, fair versus non-fair semaphores, fair versus non-fair reentrant locks, and so on. And those are exactly there. The fair property is there to avoid this type of problem, where lower priority threads never get a chance to run, or get a chance to run very infrequently. So that's the starvation problem. Another problem we talked about many times is deadlock, where you have to understand the order in which things occur, and the program depends on the right order. Another problem, which is very frustrating and maddening, is tool limitations. So oftentimes, the problems you have in your program depend on timing properties which differ if you run it in the debugger. So a lot of times if you're running it in your debugger or you're single stepping through the code, the timing properties are completely different than when your program is actually running in the wild. And therefore you can't actually detect the problems when you're trying to debug it. Boy, is that frustrating. And that's sometimes called a Heisenberg bug, where the act of debugging actually causes the system to change its behavior or state. So that's a big problem. Tools make it hard for this. The best thing you can do here is typically have some kind of counter that's very lightweight. But chasing down these kinds of problems is really tricky. And there's also static analysis tools or dynamic analysis tools you can use with concurrency that will help to some extent. But those are usually more specialized and they don't come bundled with your compiler environment. Yes?
I have a question on the starvation kind of aspect.
Yeah.
Are there tools in the hardware, like scheduler in the hardware, that will kind of account for that? Do these programs use that?
Great question. So the question basically is, what are some ways to handle starvation? So one thing that is often used, and this is often used in time-sharing systems, like an operating system that schedules processes to run. What they'll typically do is they will age the priority of processes so that the longer they run, the lower their priority becomes. And the idea is to try to have it be the case that long-running tasks or long-running jobs or whatever you want to call them, processes, threads, are aged over time so that eventually other people get to be higher priority, right? So that's a typical technique. Having said that, of course, if you run your programs in real-time mode, then they don't age things, because in a real-time environment, the highest priority, real-time doesn't care about fairness, it cares about response of high-priority things. And so as a result, in that case, the high-priority threads always get priority. So it kind of depends on the system you're building, but there are ways of doing it, and aging is one way to do it. The other way to do it is to use things like the specific notification pattern techniques where you order things in a fair way. But the key thing to remember is that there's a trade-off between fairness and performance. And so if you really want things to be very performant, you may give up on fairness and so on. Yeah. It's funny how life often emulates computer things, right? If we want a society that's fair, we have different set of rules. If we want a society where people can maximize their utility or whatever, right? So there's all these trade-offs. People tend not to worry about unionizing threads, though, right? It's a little different. Some of the problems that we just talked about can be fixed by applying built-in monitor object mechanisms. So, for example, the race conditions that we've talked about, those can be applied by using the monitor objects, using synchronize to try to avoid race conditions. Using built-in monitor objects really isn't going to help us with deadlock per se. You have to have other things to address that. The issue of starvation, built-in monitor objects typically queue things up in a FIFO way. I take that back. It's haphazard, so you don't really know what it's doing, but that's not really going to help you. But the race condition stuff can be helpful. There's a great article here that talks about techniques for debugging multi-threaded programs. They don't specifically talk about Java, but the techniques that they describe are worth looking into if you want more information. And that's the end of that part of that lesson.